Welcome to Section 4, Lesson 7. Across the previous 6 lessons, we built every tool we need to describe a single line on the coordinate plane, the plane itself, the distance and midpoint formulas, the slope concept, and 3 canonical equation forms. Today, we add the rules that govern relationships between 2 lines. When are 2 lines parallel, never crossing, and when are they perpendicular, crossing at a right angle? Both rules are stated entirely in terms of slope, which is fitting because slope is the geometric property that captures the tilt of a line completely. Today we lock in the parallel rule, the perpendicular rule, and the procedure for writing the equation of a line that is parallel or perpendicular to a given line and passes through a given point. First idea on the board: 2 distinct lines on the coordinate plane are parallel if and only if they have equal slopes. Same slope means same tilt, and lines with the same tilt that are not the same line never meet, so they are parallel by definition. Symbolically, M1 equals M2 captures the parallel relationship. The y-intercepts of the 2 parallel lines can be any 2 different values. The parallelism depends only on the slopes being equal. Vertical lines, which have undefined slope, are parallel to each other as a special case. 2 distinct lines on the coordinate plane are perpendicular if and only if their slopes are negative reciprocals of each other. Symbolically, M1 times M2 equals -1, or equivalently M2 equals -1 over M1. The relationship is geometric. Perpendicular lines cross at a 90-degree angle, and the algebraic statement that the slopes multiply to -1 is the algebraic translation of that geometric fact. Special case: a horizontal line with slope 0 is perpendicular to a vertical line with undefined slope, even though the multiplication rule does not apply directly because 0 times undefined is not a meaningful product. Third idea: to write the equation of a line that is parallel or perpendicular to a given line and passes through a specific point, the workflow is straightforward. Identify the slope of the given line. Compute the new slope using the parallel rule equal slopes or the perpendicular rule negative reciprocal. Use the new slope and the given point with the point slope form from Lesson 5 to write the equation of the new line. Optionally convert to slope intercept or standard form for the final answer. The procedure takes about 20 seconds once practiced and is the foundational tool for many geometric construction problems and for the perpendicular bisector concept that appears later in the course. 2 distinct lines on the coordinate plane are parallel if and only if they have equal slopes. The condition M1 equals M2 captures this. The y-intercepts can be any 2 different values, only the slopes matter for parallelism. Same tilt, different starting heights, lines never meet. 2 distinct lines are perpendicular if and only if their slopes are negative reciprocals, and 1 times M2 equals -1. Equivalently, M2 equals -1 over M1. The negative reciprocal rule is the algebraic translation of the geometric 90-degree intersection. To get the perpendicular slope from a given slope, flip the fraction and change the sign. Step 1 in writing a parallel or perpendicular line through a given point: identify the slope m of the given line by reading it off the equation, converting to slope-intercept form if necessary. The given line provides the slope reference for both the parallel and the perpendicular rule. Step 2. Compute the new slope. For a parallel line, the new slope equals the original slope. For a perpendicular line, the new slope equals -1 over the original slope, which means flip the fraction and change the sign. If the original slope is 2 over 3, the perpendicular slope is -3 over 2. If the original slope is -4, the perpendicular slope is +1/4. Step 3. Use the new slope and the given anchor point with the point slope form template y minus y1 equals mu times the quantity x minus x1. Plug in the values, simplify the double, negatives if any, and optionally convert to slope, intercept, or standard form depending on what the problem asks for. The point-slope template is the natural fit for this kind of construction because the slope and an anchor point are exactly the inputs we have. Here is the first worked example. Write the equation of the line parallel to y equals 3x plus 2 and passing through the point 1, -4. The given line has slope 3, so the parallel line will also have slope 3 by the parallel rule. Step 1. Read the slope of the given equation. Y equals 3x plus 2 is in slope-intercept form, so the slope is m equals 3. The y-intercept is 2, but the y-intercept does not matter for the parallel rule, only the slope does. Step 2. Apply the parallel rule. The new slope equals the original slope, so the new slope is 3. The new line will tilt at the same angle as the given line, just at a different y-intercept. Step 3. Use the new slope 3 and the given anchor point 1, -4 with the point slope template. Y minus -4 equals 3 times the quantity x minus 1. Simplify the double negative on the left. Y plus 4 equals 3 times the quantity x minus 1. Step 4. Optionally convert to slope-intercept form by distributing and rearranging. Distribute 3y plus 4 equals 3x minus 3. Subtract 4 from both sides. Y equals 3x minus 7. The slope-intercept form has slope 3 matching the parallel rule and intercept -7 distinct from the given line's y-intercept of 2. Step 5. Verify by plugging the anchor point into the new equation. At x equals 1, y should equal -4. Plug in y equals 3 times 1 minus 7 equals 3 minus 7 equals -4. Match. The new line passes through 1, -4 as required. So the parallel line is y equals 3x minus 7. The big lesson from this example is the simple application of the parallel rule equals slopes, different y-intercepts. The point slope template combined with the parallel slope gives the new line's equation directly. The final conversion to slope-intercept is optional but useful for reading the y-intercept and for matching the form most often expected on tests. The procedure takes about 20 seconds once practiced and is the foundational tool for any parallel line construction in the rest of the course. Here is the second worked example. Write the equation of the line perpendicular to y equals 1/2 x plus 3 and passing through the point 2, 5. The given line has slope 1/2, so the perpendicular line will have slope -2 by the negative reciprocal rule. Step 1. Read the slope of the given equation. Y equals 1/2 x plus 3 is in slope-intercept form, so the slope is m equals 1/2. The y-intercept is 3 but does not matter for the perpendicular rule. Step 2. Apply the perpendicular rule. The new slope is -1 over the original slope. -1 over 1/2 equals -2. So the new slope is mu equals -2. The new line tilts steeply downward to the right, perpendicular to the gentle upward tilt of the given line. Step 3. Use the new slope -2 and the given anchor point 2, 5 with the point slope template. Y minus 5 equals -2 times the quantity x minus 2. The signs are clean here because both anchor coordinates are positive. Step 4. Convert to slope-intercept form. Distribute -2 y minus 5 equals -2x plus 4. Add 5 to both sides. Y equals -2x plus 9. The slope-intercept form has slope -2 matching the perpendicular rule and y-intercept 9. Step 5. Verify by checking the anchor point. At x equals 2, y should equal 5. Plug in y equals -2 times 2 plus 9 equals -4 plus 9 equals 5. Match. Verify the perpendicularity by computing the product of the two slopes. 1/2 times -2 equals -1, exactly as the perpendicular rule requires. So the perpendicular line is y equals -2x plus 9. The big lesson from this example is the perpendicular rule in action. Take the given slope, flip the fraction, change the sign, and use the result as the new slope. The negative reciprocal computation is the only structurally new piece of work compared to the parallel example, and the rest of the procedure is identical. Practice the negative reciprocal flip on a few different slope values until the move becomes automatic. Slope 2/3 becomes -3/2, slope -4 becomes +1/4, slope 1 becomes -1. The pattern is quick to internalize and is the foundational move for all perpendicular line work. 3 mistakes that catch every algebra student during their first weeks of parallel and perpendicular work. Each one is fixable with a small explicit habit applied on every problem. First mistake: forgetting to take the reciprocal in the perpendicular rule and only changing the sign. A student looking at a perpendicular relationship to the slope 2 writes the new slope as -2 when the correct perpendicular slope is -1/2. The rule is negative reciprocal, change the sign a and flip the fraction. Both moves are required, not just the sign change. The fix is to say flip and negate out loud while computing the perpendicular slope until the two-step move becomes a permanent reflex. Second mistake: forgetting to change the sign in the perpendicular rule and only taking the reciprocal. A student looking at a perpendicular relationship to slope 1/3 writes the new slope as +3 when the correct perpendicular slope is -3. The reciprocal of 1/3 is 3, but the perpendicular rule also requires the sign change. The fix is the same as the first mistake, say flip and negate out loud, applying both moves every time. Third mistake: swapping the parallel and perpendicular rules entirely. A student asked for a parallel line uses the negative reciprocal rule by mistake, getting a perpendicular slope rather than a parallel one. Or vice versa, asked for a perpendicular line and uses the equal slopes rule. The fix is to read the problem carefully before writing any algebra. Parallel means equal slopes, perpendicular means negative reciprocal. Both rules are short enough to memorize once and use forever. Parallel and perpendicular line relationships appear everywhere in geometry, architecture, computer graphics, and engineering drawing because the two relationships together cover the most common ways that lines align in real-world built structures. 4 broad sectors below. In architecture and construction, building walls are typically parallel to other walls of the same orientation and perpendicular to the floor and ceiling. The right angle structure ensures stability and predictable spatial layout. Architects, structural engineers, and construction workers think in terms of parallel and perpendicular relationships continuously, and the algebraic rules from today underpin all of the structural calculations that go into building design. In geometry, the perpendicular bisector of a line segment is the line that passes through the midpoint of the segment and is perpendicular to it. The perpendicular bisector is the locus of all points equidistant from the two segment endpoints, a foundational geometric concept that appears in circle constructions, triangle centroid and circumcenter calculations, and many proofs across geometry. The midpoint formula from lesson 2 combined with the negative reciprocal slope rule from today gives the perpendicular bisector directly. In computer graphics and image processing, mirror reflections and 90-degree rotations of objects rely on perpendicular line algebra. Reflecting a point across a line uses the perpendicular dropped from the point to the line, then continued an equal distance on the other side. Rotating an object by 90 degrees swaps and negates coordinates in a way that corresponds exactly to the perpendicular slope relationship. Game engines, image editors, and 3D modeling software all use perpendicular line math constantly. In drafting and computer-aided design, all technical drawings depend on the ability to construct parallel and perpendicular lines accurately. Engineering blueprints, architectural plans, and mechanical drawings use parallel and perpendicular constructions on every line. CAD software automates these constructions but is built on exactly the algebraic rules you learned today. The skills are foundational across all of professional technical drawing. 3 things to take with you from this lesson today. Parallel and perpendicular line relationships are some of the most foundational tools in all of geometry, architecture, computer graphics, and engineering work, and the slope-based rules from today turn those relationships into clean mechanical algebra computations. First, two distinct lines on the coordinate plane are parallel if and only if they have equal slope values. The condition m1 equals m2 captures parallelism completely. The y-intercepts can be any two different values. Vertical lines with undefined slope are parallel to each other as a special case. The parallel relationship is the simpler of the two rules and only requires reading the slope from the given line and reusing it for the new line. Second, two distinct lines are perpendicular if and only if their slopes are negative reciprocals m1 times m2 equals -1 or equivalently m2 equals -1 over m1. To get the perpendicular slope from a given slope, flip the fraction and change the sign, both moves required. Slope 2/3 becomes -3/2, slope -4 becomes +1/4. The negative reciprocal flip is the single most common error point in this lesson. Practice it on several slope values until it becomes automatic. Third, to write the equation of a line parallel or perpendicular to a given line and passing through a specific point, identify the original slope, apply the appropriate rule to get the new slope, and use the new slope with the given anchor point in the point-slope form template. Optionally convert to slope, intercept, or standard form for the final answer. The procedure takes about 20 seconds once practiced and works for every parallel and perpendicular construction problem in the rest of the algebra course. The construction is also the foundation for the perpendicular bisector concept that appears in geometry, where the perpendicular bisector of a segment is the line that passes through the midpoint of the segment and is perpendicular to it. Combining the midpoint formula from lesson 2 with the negative reciprocal slope rule from today produces the perpendicular bisector equation in just a few short algebra steps. Coming up next, the lesson called Graphing Linear Inequalities, where the equation form for a line extends to inequality form to describe an entire half-plane on the coordinate grid. Half-plane shading combines the line graphing skills from the previous lessons with the inequality solving skills from section 3 to produce a powerful new visualization tool for two variable inequalities. The half-plane idea then scales up to systems of linear inequalities and to the feasible regions of linear programming problems in later courses,